I prepared hopefully inadequate number of these, so I will just perhaps distribute them somehow. They are 2 on 1 paper, so please just tear it in 2 and try to distribute those sheets somehow across all the people, so at least so that each person can see at least one of these. Just take the last one more. So the cheat sheet is just for some formulas that I will be going through, and you don't need to remember them or write them down separately, and you can just pay attention, hopefully. So let's start. I wanted to make a talk about the so-called geometrical algebra, which is a kind of formalism that is in some sort of upgrade of the normal vector algebra that we all know from the high school, but it's far more powerful, and namely it works in any dimension. It's geometrically better because it has objects that represent planes and spaces and so on, instead of trying to emulate, for instance, planes with normal vectors like we do in 3D with the normal vector algebra. And because of that, we can quickly derive some results that are nice, independent of dimension, and generally it makes for a nicer calculating framework. And by the way, that could be a part of answer to Klaus, who already told to me that this was useless and that I shouldn't be doing the talk. Essentially, this thing doesn't bring anything new, so don't expect that I will show you a formalism that will solve the Navier-Stokes equations and prove the Riemann hypothesis. No. This is just something that makes it easier to calculate the things that we already know. You can derive all the same results by other methods, so it's nothing like new in the sense that it will be some kind of breakthrough. But it's a nice formalism, and I think that counts as well, because in a nice formalism you can easily manipulate the things how you want, and you get nice results in a nice form that can make it possible perhaps to spot some crucial things that could advance understanding of your problem or something like that. So it's just a formalism, a nicer formalism. It's nothing more, but it's also nothing less. So I think it's kind of useful to have something like this. So which one of these was actually right? So let's start by introducing the objects that we actually have in the geometric algebra. In normal vector algebra that we know from the high school, we just have scalars, which means numbers, and vectors, which we can just visualize by arrows. So we have some scalar and vector. And if we think about that, it's kind of limited. So if we want to represent a direction of plane, let's say, that essentially has two characteristic directions. If I have a plane, then I can pick up two vectors, let's say these two, to represent the plane. Then we actually don't have an object that would represent it correctly in this limited system. So it's only natural to add such an object.
If you're not in 3 dimensions, of course.
Yeah, of course. That could look perhaps something like this if I visualized it, and that would be called a bivector. And of course, we can do this in any dimension for any number of vectors. So if we have 3 of them, we would have a bit of an oriented volume, and that would be called a trivector, and so on. You can imagine that this thing can continue indefinitely, but of course it would be hard to draw, so I will stop. Each of these things will be assigned a number that's called its grade, and the scalar has a grade 0, the vector has a grade 1, the bivector is 2, trivector 3, and so on. So this is very natural and very simple, but it helps to talk about these things. So this is the list of objects that we use in geometric algebra, and there is one little catch. Instead of using just these objects individually, we can also make linear combinations, and that's a thing that can be quite mind-boggling at first, because we can do arbitrary linear combinations of these. So we can, for instance, add scalars and bivectors, or vectors and trivectors, or whatever we want. And it kind of looks like it doesn't make any sense, because we are in some way adding different types of things. But hopefully I will be able to convince you a bit that it's not as nonsensical as it looks. And by the way, if we want to have a formalism that would do new and nice things for us, then we just need to add some kind of such a catch, something new that would differ from what we had before with the normal vector algebra.
So are they antisymmetric, the combinations? Should I think of
Yes, I will very shortly get to that. So let's look at the vectors first, because we know them, so it will be very quick. We already know a dot product for vectors, which is a very simple operation. We do vectors. And now we, of course, know that this dot product is symmetric, it is linear. So these are very nice things, and these work as well in geometric algebra. And of course, if we are in the Euclidean space, then we have the high school formula like this, which essentially says that the dot product is the projection of one vector to the other times the length of the other. So this works just in the same way as we were used to in the normal vector algebra. And I think that it needs no more explanation, because everything works just like you are used. And then there is another operation that is sort of borrowed from differential forms, and that is the wedge. We can wedge two products like this, two vectors like this, and the wedge satisfies all the things you would expect from a wedge. So, namely, it is anti-symmetric. So if I switch these two, I will get a minus sign. And because of this, I also get the very basic thing for wedge product, that wedge of two vectors is 0. The two same vectors or two collinear vectors is 0. That just follows from the anti-symmetry. And of course, this product is linear as well. However, we need to make sure to know what kind of these things these two operations produce. So the dot product makes a number, so it is a scalar. But the wedge product makes a bivector from the two vectors. And essentially, we can visualize it as, if I have the two vectors, A and B, like this, then if I move the vector B along the vector A, like this, it would trace some kind of parallelogram. And essentially, that parallelogram would be the visual representation for the bivector. So this is the kind of operation we can visualize for the wedge product. And with this image, it is also very natural to see that the wedge of two collinear vectors is 0, because we are just moving them one along the other. And we trace no area. So we have these two operations, and so far we have just shown how they work on the vectors. But of course we have different things here, many more different things. So we need to somehow extend these products to work on any kind of these vectors. And one thing that will be very useful for that, and actually one thing that will give the geometric algebra the, let's say, the needed difference for being something more than the normal vector calculus, will be the third kind of the product, and that is called the geometric product. And in difference to these two, the geometric product doesn't get any kind of symbol. So we just write the two things that we are geometrically multiplying next to each other, just like with normal variables. And this geometric product with vectors produces one of those things that I talked earlier about, a linear combination of various types of these vectors. Actually, it produces a sum of dot product and the wedge product of these two vectors. And by the way, this works only for vectors. Everything that I've written in here. We will be extending these operations to the other things quite shortly. But before we do that, I would like to give a little bit of example just to show that this thing makes some sense, perhaps, and to tie it in with other things that we already know. So for now, we will just remember these three things, and let's jump right into it. Let's have a look at a normal Euclidean plane. Oh, perhaps well,
But it seems to me that this can equivalently be described in terms of differential forms. So what's the advantage with here we're talking about vectors instead of you can do all of this with differential forms. What about the scalar product? Well, wow, okay, scalar product is
yeah, you need to put the scalar product on it. But essentially, yeah, you can simulate all of this with tensor analysis or tensor calculus.
Yeah, it seems like a special case of tensor.
Mathematicians call this Clifford algebras.
Yeah, but what makes it different is this thing, this geometric product. And of course, you can just make a higher dimension tensor space and do everything in it. But
you consider formal sums like differential forms of different degrees.
Yeah, but essentially the advantage is that first of all, you can add different grades of things together, which will be quite powerful, as we will see.
And it's just like working in a tensor product.
Yeah, and essentially, if you just make a sufficiently large linear space, then this has the only advantage of being nicer. You don't need to push huge matrices around. And this has geometrical meaning, so you can get some insight into it. But of course, you can simulate it by matrices. Here some more or less huge matrices that you would push around, do with the linear operations. And because everything I've shown here is linear, so you can do it with some kind of matrices. The only thing is that using those matrices will just obscure what is actually going on geometric.
Exterior algebras are a bit different because you don't have a scale, you don't need a scalar product there. You don't need to have scalar product. Once you have a scalar product, you have a bit more. You have a bit more structure, so you can have a slightly different algebra, and this is called Clifford algebra, I think. geometric algebra equals Clifford algebra.
But it's all a special case of tensor algebra.
Yeah.
Yes, of
No,
course.
yeah, it's in fact you have the tensor algebra, and you have some ideal in this algebra, and you factorize, and then you get either an exterior algebra or a symmetric algebra or a universal algebra or a linear algebra or a Clifford algebra or maybe some other algebras
Right, I just don't,
also.
at this point, I don't see the need for a completely new language for something that's a special case of something.
Yeah, well,
Okay, anyway.
let's see what happens. Either it will convince you or it will not, and you can join Klaus, who is not convinced. By the way, I'm not really that good at differential geometry, so essentially looking at things by this point of view at least makes some of those weird pieces fall into their places. So that's why I like it, perhaps more than I should have, or I don't know, but I just like it. So let's try to have a look at the Euclidean plane with two orthonormal vectors E1 and E2. And these two vectors will have, of course, these properties. E2 times E2 is also 1 because they are orthonormal. And we get this as well. So now let's look at how the geometric product behaves. If we just do, let's say, E1 geometrically, then the wedge product will vanish because we are reaching two of the same thing, and the dot product is what remains, and the dot product is 1. So we actually get this. And if we do this geometrically, then because they are orthogonal, then we get rid of this dot product, and the wedge product is the only thing that remains. So we get that it's actually this thing. And there is one nice consequence, and that is that if the two vectors are orthogonal, then this geometric product actually entitles. Normally, for any general kind of vectors, it wouldn't commute nor enticle, because it has some sort of commutative and anti-commutative parts that would get mixed up somehow, and it wouldn't be neither of them. But here we get that we can just switch around the order, and we get a minus because of the anti-symmetry of the wedge product. So let's now try to see how this E1, E2, which is the unit bivector, essentially the basis bivector of this plane, how it behaves. So, for instance, let's calculate its square. It will look like this. And now we can use this rule that the geometric product of orthogonal vectors is anti-commutative, and we can jump with this E1 here for the price of the minus sign. And then we just have E1, E1, E2, E2. And E1, E1 is 1, E2, E2 is 1 as well, so we get a minus 1. So here we have obtained some kind of thing that squares to a minus 1, which is kind of interesting. And actually, the E1, E2 is some kind of a volume element in this plane, and I would call that a pseudo-scalar, because, well, I think that is a nomenclature that is in use already. And often we would denote it by R. And this notation would be used in any kind of space, so the pseudo-scalar would always get the I symbol. So here we get something called I that squares to minus. So there's, of course, the question if this has something to do with complex numbers.
Yeah, so let's not switch the order of these guys. So instead I get E1, E2, which is E1 wedge E2, and then I have to do, this is an object in the algebra.
Yeah,
And I have to do the geometric product with another E1, E2.
yeah.
So normally, well, at least if that's a wedge, that's 0. So how?
No, it's not a wedge. And
Yeah, it's a geometric thing. So then you have to, what you have to do is a bivector scalar product with a bivector, and then you have to do a wedge, which is 0.
well, it does some sort of thing that we will come to a bit later, but essentially, if you just geometrically multiply two bivectors, then you get something that will have a scalar part, and that will be some sort of dot product between those two things, and then it will have a bivector part and a four-vector part, and we would be able to show that those parts will actually vanish.
Yeah.
And what would be left in here is essentially something like E1 wedge E2 dot E1 wedge E2.
Yeah, which we also don't know what it is. You haven't defined the scalar product for bivectors. You haven't defined the geometric product for bivectors. So we're still missing.
Yeah, we're still missing.
Right.
I'm just trying to.
What we can say, how do we know it's associated?
Yeah, that's what
Yeah,
I was
essentially-
wondering. So we should prove that that you can switch the order or any.
Yeah, of course, but normally you would take the geometric product as the basic product, as more or less the only product that you have, and postulate that is linear and associative, and then you would define these dot and wedge express by just doing combinations of these geometric products. I'm just not trying to do the axiomatic development in this full generality because that's first a little bit boring, and then second I don't have enough time for it. So I'm just more or less stacking the features one on another.
Fair enough.
Just to give some picture. And I guess that we've killed a lot of time by this.
But this is completely isomorphic to different algebra gamma matrices, right? You can
Yes,
replace the piece with gamma matrices. So yeah.
yes, you will. Actually, that is one thing that I wanted to show later, but essentially that is what made the gamma matrices make some sense to me. Because before, nobody ever cared to explain what the gamma matrix was. It was just some random matrix full of random numbers that had some algebraic properties, and random vectors of four things were being pushed around in the calculations. And this at least makes some geometrical sense. So that's one thing that is.
Okay, but you're not completely fair to Clifford algebra because you don't have to think of the Clifford elements as matrices. You could, they're just some elements, you call them E1 and E2. And that's exactly the same as.
I get the same thing.
Yeah.
The gamma matrices are faithful representations
Yeah.
of the Clifford algebra. Yes. Representation, and you have different representations.
Yeah, of course. But this gives a nice picture, and essentially, yes, it is equivalent to the Clifford algebra.
So the geometric algebra means that it's a special Clifford algebra for this regular scalar product in three space.
Yeah, I guess.
Okay.
Or you can just do it in any dimension, but these two are more or less equivalent, I think, because I don't really know what the Clifford algebra is. So the explanation of gamma matrices as a representation of Clifford algebra is not helpful for me.
Okay.
And
The scalar product you use for gamma matrices is Minkowski scalar product.
yeah, I know.
This is the regular one in space.
Yeah,
That's
Well, you
what,
can use any.
that's what your space.
Any signature.
Yeah, you could use any scalar product you want.
and you can use any scalar product here that you want. Now, perhaps let's have a look at I once more. What it does if we multiply it with E1, for instance. That would do this, and we know that E1 is 1, so we just get an E2. And if I would do that in the other direction, or for the other vector, E2, fluid space, then of course I would get this, and after jumping with the E2 over the one vector and getting a minus, we get that it's a minus E1. So if we multiply the E1 and E2 by this I from the right, then this thing gets rotated like this. Here we have IE1 and here we have IE2. So in this regard, this
That is the other way around. It's I should be from
oh,
the
right,
right.
so of course. 1I, E2. So in this regard, the I also works like the regular complex unit I. But if we switch the order, then we will get the same thing but rotated in the opposite direction. So it's not really the same. So here we can see that if we write a complex number, I don't know, let's say 5 plus 4I, then in some sense it's just the same thing as writing a sum of a scalar and a bivector. And this complex I actually is some sort of operator that turns things 90 degrees. And we get the same kind of I in here as well. So essentially linear combinations of numbers and bivectors behave exactly like the complex numbers. So this is one way how to show that the idea of adding up different things is not perhaps as ugly as it has first looked like. And by the way, this also has one more advantage because it does a better differentiation between the scalars, bivectors, and vectors. This thing, when geometrically multiplied by some vector, will just scale it, rotate it, just like a normal complex number would. But we are making the difference between these kind of operations of scaling and rotating and the vectors that are being scaled and rotated. While in normal complex numbers, what we are working with is essentially only this operation of scaling and rotating. So in this way, we also get a very little bit of geometrical insight in what's happening. Of course, when we multiply complex numbers, then we are just making composition of those scales and rotates. And if we would use that on some unit vector, let's say that E1, then we would get just the same behavior as we are used to. So actually we could and can do the vector manipulations just by using vectors like complex numbers and these operations like complex numbers, but this is a bit more geometrically faithful, let's say. So now it is time to.
So, is it somehow important that you are summing objects of order or whatever it's called different by 2 because you are summing scalar and bivector, which is like
Yes.
0 and 2. Can you sum 0 and 1?
Yes, you can.
Okay.
You can do any linear combination you want. This will very often happen that they will differ by 2, and we will shortly show why that happens. Essentially, the geometrical product is what does this thing. That it naturally gives a sum of objects whose grades differ by 2.
But it's also important that the ideal is even. That when you do AB plus BA, then it's a scale. That's the relation, and it's of even order.
So now we can just go and extend this operation to higher dimensions and higher order of those vectors. And essentially, because we want to start with the geometric product and derive the other operations from it, then I will just write down a kind of formula that will, for instance, help us to do a dot product or wedge product between a vector and an arbitrary k vector. So let's do it like this. And I will write that down in terms of those geometrical products. So essentially here we get, and here we just take the geometrical product as some kind of opaque black box. Just the basic operation that we can do, and that behaves essentially on the basis vectors. It behaves like we have seen before. Just we can calculate anything by jumping with vectors and using the rule that, for instance, E1 squared is 1 and so on. And what is left behind is just what we keep. So we just push things like E1, E3, E4 as basis objects. This would be some basis trivector of perhaps a 4D space. So let's continue here. Here we do a similar thing with the wedge. And these formulas should be the cheat sheet so that you don't need to memorize them too hard. Essentially, requiring this to work on the wedge product is kind of nice because then we can build up these multivectors from wedging individual vectors together. And then, of course, when we consider how those vectors can sort of jump one over another, then we get just the same kinds of rules that we get, for instance, in differential forms, where we have K form and L form, then actually switching them will give a factor of -1 to the KL. And the same thing works in here, because we are deriving the same thing just by moving two groups of those products one over another. And that's why we switch.
That's not only L instead of K. Maybe only the grid of the second wedge.
Yes.
Second form.
Yeah, here the A is just a vector.
Just a vector. They have grade 1.
No, I mean, eta L. The formula shouldn't be -1 to the L.
No.
No, because
It's not-
you need to take L vectors and jump over K vectors. So each of the L vectors makes k jumps, and you get KL jumps together. So essentially, this is the reason for having this weird factor of -1 to the k in here, and the dot product will just get it as well, just with the opposite sign, just to keep the same convention.
Do I understand correctly, these two equations somehow define the scalar and wedge products in terms of that postulated? Yeah, so now we are switching to the axiomatic kind of way of thinking. So we are getting from the.
Yeah, I'm kind of switching around because I have little time and I need to show at least something.
Maybe it would be useful to take bk as another vector. Then you could see that AB plus BA is twice the scalar product of A and B.
Yeah, it will work for vectors because, of course, it has. And but
basically, you can extend this relation. That's all you need, this one relation.
Exactly. And essentially, what will be very helpful for us, and now I will state it, is to realize that using this dot product on the dk will lower its grade by 1, while wedging will increase the grade. So here we have taken a grade k object, and dotting it will result in a k-1 grade object. Wedging will make a p+1 grade object. So these two things actually increase and lower the grade. And of course, if we just add them up, we get that the sum of those two things is once again the geometric product of A and BK, because those two things have the opposite sign. So when we add them, they cancel. And this is how the geometric product of a vector and a grade k object can work. So with this formula, we actually come at an interesting thing. If we have a grade k object bk and we multiply it with some vectors from the left, for instance, then each of those multiplications will sort of split the grades, and after doing the first multiplication, we start with a grade k object. After doing the first multiplication, we obtain the sum of these two things. So we obtain the sum of k-1 grade and k+1 grade object. When we multiply again, then the same thing happens with each of those two things. So we get k-2 grade object, k grade, and k+2. And by multiplying more and more, we get a bigger and bigger ladder of these things. And by the way, Thomas, that's why these steps of grade 2 happen so often, because the geometric product will make them just very naturally in this way. Of course, this will stop when we arrive at the grade 0, because then multiplying by anything won't make the grade -1, that would be nonsense. And similarly, when we arrive at the dimension of the whole space, then we cannot have a vector that would have greater grade than the space itself.
So what happens then? Do we get 0?
Yes, you get 0, like in differential forms, because when you wedge, let's say, 4 vectors into 3D, then one of them is certainly dependent on the 3 others, so it will just vanish. So this is an important thing about the geometric product. And by the way, if we ever wanted to multiply just general K and L vectors together geometrically, geometrically we can do it, but if we can do it, if we want to do it, let's say with a dot product, then we just can define it as, and now I will introduce a new notation. These angular brackets just mean that we take a grade, the part of the thing in them that has the grade here in the lower index. So, for instance, if I just do 2 plus 5 E1 which 2 and took the second grade part of it, it would discard the scalar and keep the bivector. This is nothing more than just a simple projection. Of course, if I would take one vector part, it would vanish because there is no one vector part. So this is a new kind of notation, but it's that simple. And essentially, the dot product is defined as taking the lowest grade that occurs in geometrical multiplying those two things. If we imagine the ladder that I drew and wiped out, then the dot product will just grab the lowest point. Similarly, the wedge product will grab the highest point.
So if you mix the dot product and the geometric product, are they associative in between each other? They're not.
The wedge product is associative and the dot product is not.
Together with the geometric product, that's what I was thinking. You have it like, A, geometric product B, dot product C, geometric product D. Can you do this in any way you want?
No. You need to just keep track of what's being done first and what's being done second.
So what is being done first?
Well, that you have to know when you write down the expression.
Okay,
Right?
so it depends.
Yeah, you need to, if you would have this, then you would need to use some parentheses to show what's going first.
Okay.
It's literally just multiplying gamma matrices. Symmetrized matrix in the first thing.
Yes, it is. But essentially, I think the point is that nobody really uses multiplying gamma matrices for solving some geometrical problems.
Sure they do. Of course they do.
Yeah.
You heard about spin factors, for instance?
Well, of course not, because
So that's a geometrical problem solved with gamma matrices. You can show that if you have a particle that you make a loop and you have some spin degree of freedom and it traces out some geometrical space angle going through this loop and you see gamma matrices.
no, essentially then you use.
You get the path ordered product of gamma matrices.
Maybe it's better to say that when you do these calculations with these vectors, with these abstract vectors, you cannot, any representation of them will have the same properties. So not only the face representation with gamma matrices, but any other representation.
Well, you don't need the representation. You just need to get
Yeah, of course.
Yeah, calling them gamma matrices sort of suggests specific
Yeah.
representation, which is what we have in mind, but you can work with them completely abstractly. But maybe the right mathematical term is clip it out. It's just, well, just clip it out.
I guess so, and people are actually referring to it as a Clifford algebra, but I really don't know what's the meaning of the term, so I didn't want to use it because I didn't know what it meant. And this is we can just show off a couple of very simple operations, and then I will show some very basic geometrical applications, and we will call it today because already 2:50, so some people will have to leave anyway. So one more thing that I wanted to show was the very simple operation of reverse, which essentially grabs a product of vectors. And if I reverse it, I will show that with this kind of dagger, then the result of that operation is just the same product, but with the order reverse. And if we extend this by linearity, by doing this, and of course, if we think about this thing, we can so get very quickly that if we reverse such product, then we get the product of the reversals, but in the opposite order. So when we do this thing and extend to any kind of those objects that we can manipulate, then we just have a complete operation that's called the reverse. And why it's useful? It's because we can do calculation of some kind of magnitude for any kind of vector or bivector, or even a linear combination of more than one of these. So we already know that if I just multiply two vectors geometrically, then we get just the dot product, and it's some kind of number that we can say is just the square of the magnitude. Then if I would like to do that with the bivector, let's say AB, then if I wrote it in this way, then the vectors would have to jump one over another, and we would perhaps pick up some sign. But if we use the reverse order here, we just get b squared a squared. And now if I get the bivector and write it as a geometric product of two orthogonal vectors, then of course I would get something like this. And this would be one of these, and this would be another. And now what I obtain is just the square of the area of the bivector, the parallelogram that I used to represent the bivector. So this kind of thing is kind of natural way to calculate magnitude of vectors and bivectors and whatever we want. If we want to extend this on any general linear combination of vectors, then we need to add one more thing. So if we have just a k vector that we want to take the magnitude of, I will just define it as ak times its own reverse. And then we have the product, and it is multiplied by the same product in the opposite order. So essentially the same vectors in the product are touching, and they just evaluate to the square of the magnitude, and it continues outwards. if I want to do this for total general multivector, then I just define it as the scalar part of this. But that's something we won't be needing now, so I will just mention it as a bit of a curiosity. But this thing is very useful because it makes it possible to do one more thing that can be very useful. And that is essentially finding an inverse for vectors or bivectors or any kind of those. So essentially, if we would like to find an inverse under the geometric product for, let's say, a k, then we would like the inverse to, of course, have this property. And using this, we can very simply find a thing that will satisfy this. Because if I grab a k inverse equals a k reverse over the a k magnitude squared, then I've just broken down essentially this definition. If I multiply ak by ak reverse, I will get the square of its magnitude, which is just a number, and it gets cancelled by the same square of the magnitude in the denominator. So this is the way how we can sort of divide by multivectors, and it can be useful in some occasions. So it's nice to have this property. And if we think more about this, we can also show that this is the only way of doing such an inverse. So the inverse in this sense is well defined, but not all linear combinations of k vectors need to have such an inverse, but either they don't have any or they have one. So that's a nice thing as well. And we can make inverses for some of those combinations as well.
So this AK squared, that's not necessarily a number, right? That's just some 2K vector.
No, it's a number. I mean, this magnitude AK squared.
So
That's a
AK is a K vector, AK inverse is also a K vector, but you take the different order.
Yeah, because if you have the vectors like, let's say, this,
Yeah.
then these two vectors multiply to scalar.
Oh, yeah, sure.
Then you can commute it away, and these two vectors multiply to scalar.
So it's always a number because of the undiscriminately, the higher order degrees would always go to 0 and you pick up all the flows.
So that's why it makes sense to talk about this thing as the magnitude, because it's just a number or square of that number. Right, so I've shown the inverse, which is a nice thing to have as well. Real, right. And now I can show a little bit of applications, which will be some very simple geometric ones that I don't know if you will appreciate. They are more like high school math, but anyway, I was lying how easily this formalism was able to cope with them, so that's right. First of all, I wanted to show how this ties in with the gamma matrices, but essentially it looks like everyone knows that, so I will just skip it. Of course, if we use this in a Minkowski space, using some 4 basis vectors that square to +1, -1, -1, -1, for instance, then if we have a look at the bivectors that this generates, for instance, gamma 1, gamma 0, gamma 2, gamma 0, I mean those bivectors that contain one of those spatial vectors and the timeline vector, then actually those vectors behave a lot like a power spin matrix. So that's a nice thing as well, because, for instance, if we multiply them, if we square them, then I have to jump with my vector still. So that gets a minus sign, and then I have gamma 0 squared, which is +1 times gamma 1 squared, that is -1. So the result is +1, so each of those things squares to +1. And if I would multiply them together, then I will just get I, where I is gamma 0, gamma 1, gamma 2, gamma 3 times the third one. So this has exactly the same properties as the power matrices. And it's nice because, at least for me, this brings more light on them. And as I said, I was just taught to push the vectors around in the calculations, and nobody ever told me anything about what it meant. So I really appreciated that this formalism was able to tell me. And so this is something that pretty much known. And by the way, one more thing. This I also squares to -1. So essentially, it looks like that in physics, whenever we have a thing that squares to -1, we just grab the complex unit I. But here we have different pseudo-scalars of those spaces that we are working with, and they are geometrically different, and still these pseudo-vectors square to -1. So it actually looks like that by just putting these complex numbers everywhere, we are just in some sort of squashing the geometrical meaning too much. But now I just wanted to show a couple of very, very basic things, pretty much analytic geometry that you know maybe from high school, because it helps to visualize what is going on in here, and that will be maybe a part of the answer why bother with this, because you can look at those formulas and you see what's happening. And I think that that's the only point why we do this, or why should anyone do this. So one such thing, if we want to do some simple geometry, then we should at least know how to write down an equation of a line or a plane or these things. But here it is very simple, because let's say that we want to do an equation of a line that has some direction vector of u, and we know one point A. So how do we do that? Well, if we have a point on the line, let's call it x, then the difference between the points, the one that we know and x, needs to be collinear with the direction. So if we grab the difference, it needs to be in the direction of the line, and that means that if we wedge it with the direction of the line, we need to get 0, because if these two vectors are collinear, then of course the wedge will vanish because of the anti-symmetry. So this is simple equation of a line in this formalism, but of course this is not really limited to lines. If we do the same thing with a plane, then we will find that nothing really changes. let's have a point A in here. And now, if I have another point X in the plane, well, the difference between those 2 points needs to lie in the plane of the bivector. So if this has a bivector V, then this wedge needs to be 0. Why? Because, of course, when this lies in the plane of B, then I can just write it as a linear combination of the 2 vectors that make up the bivector B, and the wedge vanishes. And in this way, I can represent any dimensional linear object. So it's nice that I have one kind of equation for pretty much everything. And of course, if I now wanted to do the standard things like finding intersections or whatever, then I, of course, could. But I would like to finish by 2 things that the formalism can solve very easily. And they are just very simple high school problems, but still, well, maybe not so simple. The first thing that I would like to do is the distance from a point to a line or a plane or whatever. A very basic thing, but it will be easily done in any dimension if we just think a bit of how we can make projections in this formalism. So still, let's have a line here with one point A on it and the direction U. And here we have some other point, let's say Y. We want to know the distance between the point and the line. So how can I do that? Just grab the difference of these 2 vectors. And now I would like to separate this vector into the part that is collinear with the line and the one that is orthogonal. How can I do that? There is a simple trick for it. Let's just take this vector B. And what I will do is that I multiply it by any kind of multivector, or I mean the grade K vector, and its inverse. This inverse surely exists because we have shown how it looks like, and of course, by multiplying by this, I haven't changed it. Now we can grab this geometric product and expand it as a sum of a dot and a wedge. And this gives 2 parts. And essentially, these 2 things are exactly what we have been looking for. Acting inverse.
Okay, so where are the parentheses now?
Here. And there are some sorts of conventions, what those expressions mean when I omit the parentheses, but I won't go into them right now because I just want to show you what it means. So now we can actually easily show that this thing is the parallel part, while this thing is the orthogonal part. And how can I do that? Well, I just multiply it by the K geometrically. So, of course, I see that it is equal to this, so the AK inverse cancels with the AK. We have this one. But on the other hand, we can expand the geometric product once more into this. So now I see that this, in fact, is a k-1 vector because it's just this dot. But here on the right hand side, I have a k-1 vector and k+1 vector. So essentially, the k+1 vector part must vanish because otherwise it couldn't be equal.
Well, you have this. The first thing is just the thing on the left is just the first thing on the right. So the second thing on the right has to be 0. You don't need to even compute any. Oh no, it's a dot and a geometric. Sorry, yeah, you're right. Okay, good.
Oh, maybe
Yeah, I didn't see the graph. I didn't see the.
So this shows that the D parallel wedge AK is equal to 0, and that means that the D parallel is in the plane or whatever of AK. So actually we got part of D that is in this direction. And
But so AK is special. You didn't. I thought you said AK can be anything.
why would it be special? It is
Well,
it's just an AK vector.
yeah, but you're saying it has something to do with this line.
Yeah, if I wanted to do it with this line, then AK would just be this vector.
Right.
If I wanted to do it with a plane, then I could
But
do it.
when you
with-
said it, it sounded like I wanted to have something to do with this vector, and I just use any AK. That's fine. I can use any AK, and it still will be associated with this. That's the way it sounds.
Ah,
But,
sorry.
Like a general formula, but you can do planes and formulas on the board. But you can do this as well, I think.
Yeah, this
And
is
it becomes more geometrically intriguing if AK is a multivector, having all kinds of terms in it, from
yeah, but
0 forms to K forms, or you want it to be a K.
then the problem is that this separation doesn't really work. So
I think the hidden problem is that not every this AK can be written as a product of A1 vectors. In dimension 4,
it breaks down
fails.
because
Fails.
you can't do, for instance, E1 which E2 plus E3 which E4 can be vector.
Yeah.
But this is not really relying on that factorization.
No.
So anyway, this shows that the parallel is actually in the same direction as AK. And by just the same kind of argument, just by taking the orthogonal, we could show that the orthogonal is actually orthogonal to the AK. So I have truly separated the vector D in two parts. One is parallel to AK and one is orthogonal. So I have truly obtained what I wanted. And now getting the distance is very easy because this vector is the D parallel. And if I want to do the distance between the point and a line or plane or anything given by the vector AK, then of course I just need to take the magnitude of this vector, which is just the required distance. And because I already know what the vector is, it's this thing. I'm more or less finished with calculating the distance, so I can write it more nicely like this. And if you look at it, it kind of looks like all those usual formulas that we know from high school, but this is completely general. It works in any dimension, and it can calculate the distance of a point from any kind, k-dimensional linear object in any dimension of space. So,
would some practical calculation be accelerated by this? Like, for example, if you take some particular example, for example, some two vectors in a 4D space, and some point with some given coordinates.
yeah.
Do you think you could calculate it this way faster than by some more traditional approach?
Well, I think it would be quite even, because still the traditional approach is, well, maybe it depends. If I wanted to find the distance of a point from a three-dimensional space in 4D, then this wouldn't be really quicker, because in the classical vector algebra, we have the nice formula for the distance of a point from any n-1 dimensional thing. So in that case, this wouldn't be any quicker, but if we wanted to find a distance from a point to, let's say, a plane in 4D, then I think this would be better, because you would have to first find the formula in 4D, and it would be something different to what we do in 3D or 2D. It's nicely, I think it nicely shows in 3D as well, where you can calculate certainly the distance of a point to a line, but the formula looks different to the formula that you have in 2D, because you use a different kind of equation for the line.
Maybe it would be nice to show such an example, like, I mean, not now, but when you talk about it at some other occasion, and that would be very convincing. It's really very fast.
Yeah, well, the problem is that we are running out of time.
What about if the plane is not through the origin? Don't you have to do some extra stuff? I mean, one thing is to say something.
No, because the D is essentially the difference between the point that I'm searching the distance for and one point on that object. So essentially, what needs to be here to be completely clear is y minus a. And now it's working regardless of whether it's going to be or not.
The problem with this is that you only need the exterior product and the magnitude. So you could do this only with exterior algebra, this calculation, and knowing how to do magnitudes of k vectors.
Yeah, I guess you could, but on the way we use the geometric products that you don't have in exterior algebra. So if you were doing this in exterior algebra, then I guess you could get the same thing. But I don't think the derivation would be as simple as this.
Probably not, but there is a lot of things you have to do beforehand in order to do this calculation, right?
Yeah,
You have to define the Clifford algebra and so on.
but still I think I have a comparatively small amount of material that enabled to do such a calculation that is quite simpler and not.
I think actually graphics card compute, you have to compute a lot of products and distances, and they actually use the projected version of such formalism.
Yeah, it's
Using-
very possible because
They
I don't know.
Because in 4 dimensions you can use quaternions.
Yeah, quaternions.
Yeah, but it's just a coincidence.
How did you get from the, I mean, how did you get the last equality?
Yeah, I get it because the AK inverse is reversed by magnitude squared. So this is a scalar, and you can quickly show that this has the same magnitude as AK. So if I do magnitude of this, then I get this. And it cancels, so I have the very natural thing that the magnitude of inverse is 1 over the magnitude. Because I was doing the product here, and the AK inverse essentially.
The inverse is clear, but I'm wondering how you combine that parenthesis with the wedge product with the AK inverse, because it's not so obvious, maybe.
It's a geometric product between this parenthesis and the inverse.
That's right.
So this parenthesis was kept, and I just wrote it here.
And in the picture, D was y also.
And the D is just the difference between the two.
Okay, yeah.
So just that the magnitude of the product
It's a product of magnitudes which.
Oh, that's what I was missing.
Yeah.
So that's what you can show. Okay,
Yeah, you can show it.
That's right. Okay, yeah.
Because
good. Yeah, that's it.
essentially.
Oh, of course. That's the missing part. Good, thanks.
So this one thing, and the last thing that I want to show is a problem that's not so simple, and that actually can be really tough if you don't know how to do it. And this distance, for instance, of 2 lines in 3D. That's the great word mimoběžný in Czech. I don't think we has any equivalent in English. And moreover, we will be able to do this for, once more, any kind of these linear objects in any dimensional space. So I think that's quite nice. And how can we do that? Well, let's grab 2 objects. And their equations will look like this. And they can be even different grades. So, for instance, I can search for the distance between a line and a plane for. And now, how do I get the distance? So, first of all, I multiply the first equation by wedging it with the L. And similarly, I wedge the second one with a K. So what I get is wedge K wedge L equals 0, and the second one, now I will just grab the NK and jump over that DL, and that will perhaps generate a sign, but since it's equal to 0, we can just cancel the sign. So I will just write it in the same way. With this. Now, if I subtract those 2 equations, I have, for instance, y minus b minus x plus a. I just added or subtracted those parentheses, which ak, which bl, still equals 0. Now I can just grab this y, x, and a and b and pull them apart. So I have y minus x, which ak, which bl, and I will put the part with a and b on the other side. So here it was minus b plus a, here I get b minus which ak, which. And now the main trick comes. I know that when I find the point that realizes the minimal distance between the two things, then the thing is the vector is to be orthogonal to both of these, because well, the distance needs to be covered in orthogonal direction. Oh, perhaps. So now if I let's try to do some of those two lines, perhaps well, that isn't a really great picture, but this vector d needs to be orthogonal to both of directions of the a and the b, which means that the d dot ak wedge bl needs to be 0 because it needs to be orthogonal to every direction in ak and bl. And now the geometric product gets in once again, because this works for any y and x, or for x on one of those things and y on other of those things. So this can work for the d as well. So I have that b wedge a k wedge bl equals b minus a wedge a k wedge bl. But because the dot product between these two things is 0, I can actually substitute it with a geometrical product, because I have d dot this wedge, and that is 0, plus d wedge this wedge. And together, they just make d geometrically times this boundary. Now it's almost done, because we have defined how the inverse works. So we can just multiply by inverse of this to get it. And if I want to get just the distance, then once again, I get the magnitude of the beam and distance I was searching for. So I just multiply with the inverse of this, so this goes in. And the great thing is that this works for pretty much any grade of A and B. So if I wanted to calculate the distance of two planes in 4D, this would do it just as easily as it would do the distance of two lines in 3D or anything else.
One of these objects cannot lie in the other.
And of
That
course,
doesn't work.
they must have all these directions different, because otherwise this wedge would be 0. And they would have a common point. So this calculation actually silently assumes that they don't have a common point. Common direction, rather. So that's everything I wanted to show. It looks like many people are not really convinced, but well, at least I tried. Yeah, of course.
Yeah, okay, so thank
If
you.
there's any question, of course, you can ask. I will be able to answer.
Can you remind me these equations for x minus a by something? So if I have a line, then that means that A is a one vector or its co-grade is one.
It's a one vector.
Okay, so whatever I'm measuring it with is basically like
Yeah,
the
it's the direction of the.
Okay, so it's not like a co-direction. Okay.
If you have a line, this is the direction of the line. If you have a plane, that's the bivector giving the plane.
Okay. Makes sense. So does anyone else have some questions? Maybe I'll ask one more thing, because it wasn't clear to me when did you differentiate between defining the product, like the geometric product as a sum of the dot and the wedge, and then you have this axiomatic definition. So
I should have said that more clearly.
yeah, so just if I just pick some dimension, like I don't know, 4 or something, and I will try to calculate, I don't know, the dot product between a 2 vector and a 3 vector. So how would I do that? So I would need to somehow axiomatically define the geometric product, and they just take the symmetric part of that, or anti-symmetric.
Yeah, well, the geometric product, actually, you will always work in some basis, right?
Okay.
If you want to do calculations, like concrete calculations with coordinates, you will have a basis. So if you have an orthonormal basis, as we were using in these examples, then it's kind of very simple because, for instance, you have the basis vectors E1, E2, and so on, and then E1, E2 is just the basis bivector in those two directions, and E1, E3, E7 is a trivector in these three directions. So these are just your basis vectors, and when you do the geometric product, then, well, the rule is very simple. You just jump the same vectors together to cancel them, and then something is left. And then something will be another basis bivector, trivector, or any vector. So,
and they always cancel with a +1 or with a -1.
they cancel with a +1, of course, if you are working in Euclidean space.
Okay.
But if you were doing some relativity, then of course you will have some of those basis vectors square to -1. Either one of them or three of them is one.
They probably don't even have to work in a basis. Just have some list of vectors multiplied geometrically, and whenever you encounter AB, you just use that it's minus BA plus the scale.
Yeah, plus 2 times the dot product.
Or whatever, or minus,
of course.
just convention.
If they weren't orthogonal, those dot products would pop up whenever you switch the two things. And that's essentially because we defined it to be AB equals 1/2 AB plus BA. So if I just express BA, then I get it's minus AB plus 2 times this dot product. So even if you didn't have an orthonormal basis, you would still be able to switch them around, but these dot products, essentially the battery would pop up in that way.
Okay. Thanks. Okay, so thank you again. If you don't have any further questions, then let's thank the speaker. I'll send an email about the next time. So depending on whether the speaker will talk for 1 or 2 hours, we'll meet from 2 or from 1 on Thursday again. So yeah, thank you everyone.